Hello, this is Introduction to Cognition. I am Benjamin Miss, and today we are talking about research and experiments. Experiments for exploring the mind. In the past, many experimental tools were available solely to those with access to tens or even hundreds of thousands of dollars. Large universities and corporations drove research because they could afford early computers and neuroscience machines. Technological advancement has led to the availability of many techniques that would have been out of the reach of most of us in the past. This democratization of the science of mind can allow for first and second year college students to perform valuable studies and present their work at prestigious conferences. It is no longer primarily about access, but about insight and creativity. Still, some techniques will be out of reach to the casual student for quite a while longer. Magnetic resonance imaging, MRI machines, cost millions of dollars and thousands to maintain on a monthly basis due to the extreme cooling measures necessary to maintain the powerful electromagnet in the machine. Each hour-long research session costs hundreds of dollars to run. Similarly, positron emission tomography machines are expensive due to the costs associated with building and maintaining positron detectors and the dangers of using radioactive elements. Transcranial magnetic stimulation, TMS, is becoming more accessible, but there are some concerns associated with changing brain function, even temporarily, and so this technique will probably remain in university labs. Other methods of science and neuroscience, some of which have been discussed previously, include psychophysics, reaction times, EEG, eye tracking, pupil dilation, and GSR. Some of these can cost nothing more than the price of a computer. Any of these can be done repeatedly for a startup cost of a few $100s. Do you know how to code? If you want to do cognitive science, learning to program simple scripts in Python or some other free programming language will give you a major advantage. Here, we will consider various methods with examples of simple experiments you can perform in order to glimpse the inner workings of the mind. Psychophysics and reaction times. Simple experiments involve having people make judgments about stimuli. Psychophysics involves something as simple as creating experiments where people view stimuli and judge whether they are the same or different. In the past, experiments were done with precisely calibrated instruments, such as a light box with two lights that differed precisely in illumination. We can calculate exactly how much brighter one light has to be compared to the other in order to be viewed as different. Today, the same type of experiment could be mimicked on a computer screen, manipulating things like color to see how sensitive our visual system is to difference. Consider these two blue boxes, whether they are the same or different. They look similar, but when placed directly next to each other, we can see a slight difference in hue. This kind of simple experiment can help us understand the characteristics of visual perception and processing. Adding reaction time measures can give us further information. For instance, as you manipulate the colors to become more similar, people are still making correct judgments, but you notice it is taking them longer. You can include a measure of reaction time and see that even though they are making the same correct judgments, it is harder to make those judgments. Psychophysics allows you to change any level of intensity of a stimulus and measure the response, providing information about subtle differences in sensory perception and processing. The sense of touch, being made up of many different senses, allows you to see different levels of sensitivity in different parts of the body. Use your imagination. Beyond the basic psychophysics, you can look at how people respond to various scenarios that are designed to elicit some kind of emotion, or measure how quickly people read and process emotionally charged words. Electroencephalogram, EEG experiments. 30 years ago, EEG was cutting-edge research that required a magnetically shielded room, carefully calibrated equipment, and expensive computers. An EEG setup in a university could cost over $100,000, especially when considering the data collection rooms could be used for little else. Today you can buy brain-sensing headbands and associated equipment for a few $100s. A multi-channel setup with amplifier and software will cost less than $1,000, and you can do EEG experiments at your kitchen table. While this expense may put EEG out of reach for many, it is still far more accessible than in the past. Most systems come with easy-to-follow instructions. However, there is still a difficult learning curve here. EEG produces thousands of data points per second, so it is important to learn to use analysis software. If you or a friend meditates or can fall asleep easily, you can look at differences in the signal under different states of consciousness. Often, just looking at the EEG output will show subtle differences in brain function in relation to conscious state. This is the rudimentary way of looking at the signal that was popular before advanced computer processing. Many programs will allow you to separate components of the EEG signal, such as alpha waves and beta waves. Alpha is greater under relaxed states, and beta is greater under anxious states. Changing tasks will give you the ability to see changes in the signal. Many programs will also allow you to calculate ERPs, event-related potentials, and steady-state responses, SSR. ERPs require repeated trials, but are fairly easy to understand. You present similar stimuli, usually in at least two different conditions, and average the multiple trials of the two conditions. All work with the EEG requires precision, so that the timing of the trials line up. The ERPs should look different between the two conditions, allowing for a neurological processing explanation for those differences. The SSR can be calculated using only a single trial and involves viewing the underlying components of the EEG signal. Still, as with typical experiments, multiple trials allows for greater confidence in the results. Pupil dilation experiments. Research has shown that when individuals engage in tasks that require updating, switching, and inhibition, increases in effort are associated with an increase in pupil size. This allows pupil dilation to be used as a measure of cognition. Specifically, measuring pupil dilation can give us a direct measure of aspects of the autonomic nervous system. The autonomic nervous system can be thought of as automatic function, where the sympathetic nervous system is involved in arousal and the parasympathetic nervous system is involved in relaxation. When we are focused on solving a difficult problem, sympathetic nervous activity causes our pupils to dilate. Measuring changes in pupil dilation can be done with eye tracking software, but can also be done with simpler methods you already have access to. Use your phone to take a video of your eye while performing a calculation that you know takes you time to do. If you can do the problem instantly, this will not work. For many people, multiplying two-digit numbers, such as 45 times 19, takes a great deal of effort. Practice recording your eye so you know how to hold your phone's camera, and be sure you have enough lighting to see your pupil. If you have someone there to help you, even better. Keep your head still, and start recording your eye, and have a friend pick two numbers. Complete the problem in your head, and when you're done, say the answer out loud, and stop recording. What you will see is an increase in pupil size while actively solving the problem, and a decrease as soon as you have the answer. Take a screenshot now of your eye before, during, and after solving the problem. Resize the images so your iris is approximately the same size in each image. Using a simple ruler, measure the diameter of your pupil to create two ratios. The diameter before divided by the diameter during the task, and then divide the diameter after by the diameter during the task. This will show you approximate changes in pupil size and allow you to compare effort under different tasks and different conditions. What else might cause changes in pupil size? Moral dilemmas? Emotional scenes? Word problems? eye tracking experiments. If you have some programming skills, you can find free software online that uses your webcam to perform eye tracking experiments. It might take a little searching, but it can be worth it. Eye tracking is a powerful method that allows us to see automatic responses to stimuli. We often think that we are choosing where to look, yet often our eyes move before we are consciously aware of that movement. Things that are biologically relevant draw our attention before we are consciously aware. This can include both people we are attracted to and threatening situations. In many cases, people can't help where they look and often immediately look away. Cheap systems are available for just over $100 that mount a camera to your laptop and integrate it with your screen to allow you to show stimuli and see where your eye moves to. Eye tracking is useful in advertising. Studying what draws your attention can allow advertisers to figure out how to market to you and how to create packaging that you can't help but notice. Once you notice the product, what can the advertiser do to keep your attention and get you to put it in your cart? Some interesting research shows that when shown paintings that have multiple possible interpretations, you can predict which interpretation that person will choose based on where they look. You can see what draws their eye, and how experience and personality can influence where people look at various scenes. Eye tracking is as close to reading the mind as we can get. Remember, I can't look at your eyes and tell if you're lying, but with an advanced eye tracking unit, we can tell what draws your attention, which gives us a lot of information about your mental world. Galvanic skin response, GSR experiments. GSR is the most commonly used term for electrodermal activity, EDA, a measure of changes in electrical conductivity of the skin. When your pores open and you sweat, the electrical conductivity of your skin changes. GSR can give information about physiological arousal, which is why it has traditionally been used as part of lie detector tests. We can't always see you sweat, but we can detect it. Combined with heart rate, GSI allows to see if someone is excited or nervous. The reason lie detector tests cannot be used to prove guilt is that people can have a heightened sense of arousal for many different reasons. Being accused of a crime is enough to create a heightened, unstable state of arousal in most people. Emotion-evoking images, moral scenes, music, and other environmental factors can change our skin response. Anything that excites you or makes you afraid can lead to increase in sweat and skin conductivity. Relaxation or boredom can lead to a decrease. Students have looked for changes in skin conductivity by playing scary music or watching jump scares. But there are many ways to use this tool as a window into your emotional response. Performing experiments. After coming up with an idea, the first thing to do is to find out as much as you can. Often, research projects end with only an idea. Starting research can feel like an arduous process, and many research methods classes will encourage students to copy a published research project by completing what is called a replication. You are allowed to copy any previously conducted research, and in many ways, this is important not just for learning how to perform research, but also for validating previously conducting research. Sometimes, things that are in textbooks are incorrect. For instance, I realized a year after my first child was born that I made the classic error of accepting something as true when I could find no evidence of it myself. A classic image in many developmental psychology textbooks shows an adult making facial expressions and an infant making those same expressions, sticking out the tongue, opening the mouth, and pursing the lips. It was believed that newborns had this ability to mimic faces, and then lost it as they aged, before regaining the ability again. First of all, an infant is not good at anything. Humans are born with extremely premature brains, because if our heads were any bigger, we'd be unable to exit the birth canal. This means a great deal of development occurs outside the womb, and the first few months of life are often referred to as the fourth trimester. Newborns are basically still a fetus. Second, why would we have a cognitive ability lose it, and then get it back. For almost 40 years, it was accepted that infants could mimic facial expressions, and it took a massive undertaking of tracking over 100 infants for months in order to overturn this incorrect information. It will take decades longer for parenting blogs to catch up. Back to my mistake. I remembered the image in the textbooks, and I tried to make faces at my newborn, and got no response. Instead of questioning the validity of the research, I assumed I was doing something wrong, or that my son was tired and not paying attention. A year later, a researcher article came out debunking the earlier research, and I felt foolish. My mistake wasn't accepting scientific research. While research can be wrong, it is still often based on our best knowledge at the time. The original work wasn't bad, but it was missing certain controls. My mistake was ignoring my own questioning of the results, and so easily dismissing my own failure to replicate. Still, it was a small mistake. I could not have known that the original widely accepted research was flawed, and I am also aware that single contrary incidents do not invalidate scientific research in the same way a cold winter in New York doesn't mean we're not causing climate change. This is also part of the reason students often try research and then decided they're not interested. It takes a lot of work and a lot of time to perform good research. It can be disheartening when a study you've spent months on fails to get the results you expected. Before you go and dig through the scientific literature, it is okay to get used to the experimental process. Start with something simple, like comparing pupil size changes during two types of mental tasks, or compare reaction times between two judgments. One classic task involves what is called the typicality effect. We tend to put things into categories, sort of like the taxonomy of the animal kingdom. We know what a mammal is. We know what a bird is. When individuals do not contain the expected characteristics of their category, it can take us longer to identify them as being part of that category. If I show you a picture of a sparrow and ask you if it is a bird, you answer quickly that it is. If I show you a picture of a hammer and ask you if it is a bird, you answer quickly that it is not. If I show you a picture of a penguin and ask you if it is a bird, you probably tell me that it is a bird, but it takes you longer to do so. Penguins do not fly, and they waddle when they walk on land. They swim beautifully at home in the water. Penguins have feathers, but they are short and broad. They have beaks and small wings that function more as fins for swimming. We know there are birds, but they're not quite what we expect. The simple experiment to perform is to compare what we just described. Pick two things that share characteristics but differ in some subtle way, and see how people respond, either by asking them to make judgments, or collecting reaction time, or measuring pupil, EEG, or some other method. Recall the terminology discussed in the introduction to this text. You have to have something you change, and you have to have something you measure. This is the difference between a true experiment and a demonstration. The independent variable, IV, is controlled by the experimenter, and the dependent variable, DV, is measured. You have to have at least two conditions for your participants, and you have to have a measure of some kind of outcome. Due to the high variability in much of human behavior, it is important to have a reasonable sample size and have a control group or control condition. If you're testing a before and after type study on a single group, a sample size of 30 is often considered adequate. If you're comparing two groups, it is important to have two samples of 30 for a total population of 60. This starting place is based on a trade-off between the minimum number of subjects samples to perform useful statistics and the diminishing returns of continuing to increase the sample size. The best way to be sure, however, is to look at previous research on the topic and figure out how large their samples were. Looking at past research also assists in refining definitions. Much of knowledge is gathered incrementally, which means we're not looking to upend everything we know about the mind, but rather to address a single clear question in a new way. In order to create a useful study, we have to know how to assess the structure, arguments, methods, and results of previous studies. Critically evaluating research papers. The following is specific to social science research, though it could be useful in other fields. Sometimes it is difficult to know where to begin, and the first thing we do is clearly state a topic. You don't even have to have your variables defined yet. We start with a basic idea and find out as much as we can about the topic. One area with a great deal of research on it is eye tracking studies in marketing. This kind of research is particularly interesting to many students because it is applicable in the job market. Advertisers absolutely hire cognitive scientists. This is not a new idea. The TV show Mad Men shows scenes with researchers presenting market data in order to help design new marketing plans. Remember, we don't have a hypothesis yet. We're only trying to find out as much as we can. If you do have a hypothesis, you may find research that has already tested it. This is not a bad thing. It means you're thinking like a scientist, and you can find out more about the topic. The more you know, the better your hypothesis is. Be willing to learn and change your mind. If a student says they're having trouble coming up with a hypothesis, it tells me they don't understand their topic well enough, and they have to go back to typing in a general term and reading the papers. For many people, this is a difficult endeavor, but the harder you find this process, the more you will benefit from it. Part of the purpose of education is to challenge ourselves. Otherwise, we could just sit at home and passively watch videos. There are many databases that your school librarians can help you use, and a trip to the reference desk can save you a lot of time. I am only going to discuss the most commonly used database, Google Scholar, available at scholar.google.com. Once there, you type in your topic and be willing to change it around. If I type in eye tracking marketing, I find over 100,000 results. And in the first item that comes up has a PDF link, allowing me to read a chapter in a book that reviews market research. This is a fantastic first hit. A summary article or book chapter is different from an original research paper. But a summary, often called a literature review, can be extremely useful. The first article that comes up has two links on the right, one a PDF that is immediately available, and the other that is a link at a college or university where I am using Wi-Fi. Google Scholar takes advantage of my location in order to show me what research is available to me. Even when performing the search off campus, many links will come up. This article was published in 2008, which may be too old to use as a major source, depending on your assignment, but it can be mined for more information. At the bottom of the result is a link that says cited by 487. This means if you click on that link, you can find more articles on the topic. Recent articles on this topic include analyzing gender differences and cultural differences. The top left of the page of search results allows me to refine my range of dates. If I choose articles published this year or within the past 5 years, I can also look at the article itself and go to the references, looking for interesting papers that are older. We're not doing anything here other than looking at titles. Read titles, and if they look interesting, save the link. Create a page of links and add as many as you can. It takes no more than 30 seconds to evaluate a title. At this point, you don't want to get bogged down reading research papers. You want to find things that look interesting and collect sources. Collecting 100 can take less than 1 hour. You can even filter by whether your institution has electronic access to the papers. I recommend only focusing on papers you can access so you don't fall in love with one and find it out of reach. Now you're ready to start throwing out papers. Go to your list and click on the titles and you will see the abstract. The abstract is usually shorter than 300 words and will give you a summary of the paper, telling you what they did and what they found. It only takes 2 to 4 minutes to scan an abstract and see if it's useful. Once you start reading them, you'll see that many of them aren't really what you're looking for. If it looks good, find the full paper. If it doesn't seem useful, delete it. Now you are collecting a file of research papers that you'll read more deeply. Remember, your professors will know if you stop here and only read the abstracts. The abstracts are missing many important pieces of information necessary for critical analysis. It's time to read the articles now. You probably have at least a dozen good papers on your topic, and they contain a lot of information. One page of journal article can be like reading 4 pages of traditional text. This can be daunting. However, you do not have to read all the words. The first time you do this, it will take a while, but you will get much faster. What do your professors want to see when you write about a research paper? They want to see a critical analysis that shows you understand what the authors did and how they did it. You need to be able to describe the research and how it makes logical sense. Remember, there are different types of articles. Review articles that summarize a lot of research on a topic are useful for getting an overview on a topic, and they tend to be fairly easy to read. It's a good idea to start with at least one review article and read it without going into too much depth. By the time you finish a recent review article, you may have come up with a solid hypothesis. For instance, the first article we found was a book chapter reviewing literature on the use of eye tracking in marketing. And at the end of the article, they outline 5 areas for future research. These are free ideas. They might not tell you what your hypothesis should be, but they tell you what we don't know yet. And that can help you narrow down the rest of your search. One of the 5 suggestions states, more research is needed that investigates the relationship of attention to downstream marketing effects. While we may not know what this means, we can do searches on attention and downstream marketing effects to help us know what to study. The most important journal articles are those that describe research studies because your goal is to do something similar to what they did. You do not have to read every word. At the very least, you have to identify the hypothesis, methodology, results, and conclusion. Finding the most important points in each of these sections takes practice. The American Psychological Association, APA, creates their own style guide in order to make the process of writing research papers clear and to ease comparisons between papers. It should be easy to find the components you're looking for. The introduction comes first, after the abstract. The introduction describes the reason the study is interesting and the theoretical questions being investigated. The best types of studies take 2 competing theories and design an experiment that will support only one of those theories. You will likely find the hypothesis near the end of this section. The hypothesis will tell you what the IV and DV are, what is being manipulated, and what is being measured, and it will make a prediction about what will happen. Save the hypothesis as part of your general paper description. The methodology section is often the most important section of a paper to researchers, even though we tend to glance at the introduction and conclusion section to see if the paper is interesting. We look to see if the researchers are doing what they say they are doing. They have to define their variables, which means if you don't want to measure happiness, if you want to measure happiness, you have to define happiness. This is difficult, and many people will argue that happiness is such an abstract and subjective concept, it is impossible to measure. Of course you can measure abstract and subjective concepts. You have to define what you mean, and you have to share that information in the research paper. Here are 2 papers on the development of happiness measures, one from 1980 and one from 1993. Clearly, this kind of research has been going on for a long time. This tells us that researchers have been working on defining and refining what it means to be happy. The opposite of depression, a general outlook on life. These studies have to show both conceptualization and operationalization. Conceptualization is the general definition. In this case, what do we mean by happiness? Operationalization is the laying out of how we can observe this concept. Is it how people rate their life satisfaction? Is it how often they feel sad or depressed? These definitions can appear to be closely related, but that is not always the case. One is the general meaning, and one is how we can observe this concept in people's behaviors. Once the concepts are defined, the next step is to say how we're going to measure those things. Often, this work has been done for you. If you're measuring happiness, you can look for a recent index that has already been created. Is one question enough? Can you say, rate your happiness from 1 to 10 and get a good measure? Often, a series of questions gives us a better measure. Just like with measures of depression, symptoms vary. Some people might get less sleep. Some people might eat less. Some people might do both. Being able to understand the various aspects of a concept allows us to create better measures. Indexes give us a series of questions which we can then use to compare people with different scores. When you read this section of research papers, it is important to be critical. Did they do a good job with their measures? Did they miss something? Can you do better? If someone created a good index or scale to measure what you want to measure, you can use what they created in your own study. You just have to cite them, the same way you cite all the information you use in your own research write-ups. The next two sections are often read separately, but they involve the information they collected and their interpretation. These are the results and conclusions sections. Results can often be bogged down with numbers in statistical analyses. There are two key things to look for in this segment in most psychological research papers. One is what is called p-value and is used as a rough indicator of whether or not the researchers found a significant difference. There has been debate for decades as to whether this is a good way to perform analysis, but no other proposal has caught on for long. The researchers will report this p-value, and they will interpret it as significant or not significant. If the value is significant, they will state they found something. In creating a scale of happiness, the researchers might say they did a good job by seeing if people who scored high on happiness also scored low on depression. The second part of the analysis is effect size, which we can interpret as telling us how much we should care. A large effect size is generally better than a small one. In fact, a significant p-value with a tiny effect size is often uninteresting. People often ignore effect size and simply look for whether the results are statistically significant, which means they are missing out on understanding whether the findings are particularly useful or may fail in replication. A good study will provide enough information that you could personally recreate their study and get the same results. A small effect size often means it's less likely you'll also get significant results. A large effect size means we can often use the results to predict people's behavior. Most research does have significant results because journal editors prefer to publish studies that worked. This is problematic because it means there have been countless studies that didn't find what they were looking for and never got published. Unfortunately, a study can be well designed and provide valuable information, but never seen. The researchers will then summarize the results and explain how the results match their hypotheses. Often, they will give you suggestions for what to do in your own research. They might suggest areas for future research. Once, I heard a famous researcher ask a presenter, "What do we know now that we didn't know before?" Was the article useful? If so, go back and look at all those articles that cited it, and use that as your base for finding more articles. Look at who they cited, and check out those articles too. For example, answer each of these questions about the article. What was their hypothesis? What did they say they were going to do, and how well did they do it? What did they find? What would be a good study to do next? The more you read, the better you can answer this question. Where do you think the research in this field is going? I once heard a researcher say that the best way to produce publishable work is to figure out where the field of research is going and get there first? Can you read the recent articles and consider future directions and see what kind of experiments people would find interesting and useful? You can perform research. Your insights are valuable. It is not uncommon for undergraduate students to come up with ideas that excite their research professors, producing collaborations, presentations, and publications. Thank you. I hope you've enjoyed our discussion on experiments and methodology, and I look forward to more discussions about cognition.